Mixtures are physical combinations of multiple compounds and or elements. There are actually two different types of mixtures. We have homogeneous and heterogeneous. The prefix homo is Greek for same, and the prefix hetero is Greek for different. So when we're talking about homogeneous versus heterogeneous mixtures, we're talking about their consistency. So a homogeneous mixture has the same consistency anywhere you get it. If you obtain a sample right at the surface or deep down at the bottom, it will contain the same number of particles that you are examining. Heterogeneous, on the other hand, would be different throughout. You might have a higher concentration of whatever at the bottom that you do at the top. And that's the major difference between them. Some very easy examples to kind of keep in mind would maybe be like the ocean for homogeneous, and then for heterogeneous you'd maybe have like sand and water. Sand and water you can swirl around, but if you give it enough time, that sand will settle to the bottom. Therefore, there's a greater concentration of that sand at the bottom. So let's talk a little bit more about homogeneous solutions, homogeneous mixtures. They are also known as solutions. So when you're talking about any homogeneous mixture, you're going to more commonly hear it called solutions. And here we just have a picture of a regular ocean picture. So it's just your ocean here. And the ocean is a liquid solution with salt dissolved in water. To the right, though, we have two different pictures here of things that you wouldn't really suspect as much as being solutions. And they're a very specific and special type of solution called an alloy. An alloy is a solution of metals. And in those metals, we've brought out the best properties of both by melting down the metals and mixing them together. At the top here, we have a picture of brass. And at the bottom, what's used for fillings is something called amalgam. Amalgam, rather. And that's used as your fillings. The great thing about alloys is that they're everywhere. You've probably heard of plenty more examples, like bronze, for example, or the chrome tire or chrome wheels that some people have. These bring out the best qualities of the metals and get rid of the worst qualities. A commercially incredibly important one for us is steel. Steel has the strength of iron, yet doesn't go through that same rusting process. And that rusting process greatly reduces the strength of the iron. So steel is commercially very important to us. Heterogeneous mixtures, though, like I mentioned before, are different throughout. On this diagram over here, you'll note that if you just focus on the sausage here, the sausage is not evenly distributed throughout this pizza. In fact, there's a great concentration of that sausage toward the bottom of this pizza, on the bottom side. Now, that's not to say that there is not an equal amount of, say, sausage to pepperoni, but what it is saying is that with every bite you take at random, say you take a bite right here, or you take a bite right here, you're going to get a different amount of sausage. You're going to get a different amount of pepperoni, or cheese, or sauce, or whatnot. Because of that, this is considered a heterogeneous mixture. And heterogeneous mixtures are not the same throughout. Now, when we're talking about separating mixtures, there's several different means. With distillation, we're talking about a homogeneous mixture, or a solution. This is to separate out two liquids with different boiling points. To quickly explain this, you start here at the beginning with a mixture. Now, salt water is not a great example. A better example would be maybe water and alcohol. And those two are in that mixture together, and they can't be physically separated by looking at it or pouring off one or another. And so what you do is you apply heat in this flask right here. And you heat it up, you heat up the solution, until one of the boiling points is reached. So for simplicity's sake, let's say that water has a boiling point of 100 degrees Celsius. And the alcohol, let's just say, has a temperature of 70 degrees Celsius at which it boils. As you heat up this mixture, once the mixture hits 70 degrees Celsius, the alcohol will start to evaporate. And as long as that heat is kept somewhere in the range of 70 to 100 degrees, none of the water will evaporate. So as the alcohol evaporates, it will take the gaseous form right here. and a gas completely fills its container, so it will start to hit this region here. Now with this region, this tube here, that's called the condenser region. And cool water is run through that system in a closed system so as not to mix with the gas, and in the process cools down that environment quite a bit. Well, because that gas has just gone above its boiling point and turned into that gas, it's very, very close to recondensing, which it does here. Gravity takes it down through this tube and drips it back in. Now again, in this particular case here, we're not talking about pure water as our distillate, we're talking about the alcohol. The water would be left behind over here. This is, in essence, what every distillation is about. It separates out two components based on their boiling points. Another way to separate out homogeneous mixtures is with chromatography. The prime example would be chromatography of ink. Ink is not one color. Though you might look at a black ink pen and see just black, what really is present is several different pigments that have come together to make one black color that you see. Over here on the left, we have a diagram of the complete setup for chromatography. The mark has been left at the bottom of your chromatography paper, whatever it might be, and it's placed in a solvent. Most of the time we're talking about water for water-soluble inks. And that that paper is then placed just barely into the solvent. And then capillary action takes place. And the capillary action pulls that liquid up the paper, and as it moves up the paper, it runs through the ink. As it runs through the ink, it separates out the components. The smaller particles go further up. The larger particles stay further down and cannot move as fast. The two major components that we're dealing with here are the mobile phase and the stationary phase. The paper, because it never moves, is stationary. The ink and the water, as they arise, are considered to be mobile. Filtration is a separation technique used to separate out heterogeneous mixtures. So now we're talking about heterogeneous mixtures. We've switched gears a little bit. We've moved away from those homogeneous mixtures. Now the key components here are the filter paper and your funnel. Now the filter paper is porous. It contains tiny little holes, and those tiny little holes allow some things through and not others. Well, because we're talking about heterogeneous mixtures here, we're talking about big particles, and those big particles get trapped by the filter paper, allowing the water to go through. What's left behind is your residue, and what you get afterward is your filtrate. Again, these are used for heterogeneous mixtures. Sand and water would be a prime example of something that you might filter. A poor thing to try filtering would be ocean water, because the particles that make up a solution are much, much smaller than heterogeneous particles. And these particles wouldn't get trapped, and the salt would go through with the water. The last separation technique that we're going to talk about is crystallization. And this is a very simple technique of evaporating off a liquid and leaving behind the solid. So this could also be used for homogeneous solutions, but it could also be used for heterogeneous solutions. This one works both ways. The diagram over here at the right is a picture of a saltwater solution where the water has been evaporated off, leaving behind tiny salt crystals. And those tiny salt crystals are extremely pure, as is the case with all crystallization. The products that are left behind are extremely pure. We will work with these separation techniques next week as we conduct a lab where we're going to be using 3 out of 4 of them. Please bring any questions you have about them to class on Tuesday.